Hi, Chem students. It's time to talk about the second law of thermodynamics, a little bit more on entropy as well. So let's get started. So the second law of thermodynamics can be written down in many, many ways. And I'm going to tell you a few of them here, but we're going to focus on one because it's going to allow us to expand on what we do know and use it to come up with a way to predict the spontaneity of a process. And that's our goal. Thermodynamics' goal for us as chemists is to predict whether a process is going to happen or not. So here we go, some second law of thermodynamics statements. Processes proceed in a natural direction. We've been kind of running with that one as the main idea. There's also this idea that the entropy of the universe is always increasing. Okay, how about this one? Perpetual motion machines of the second kind are impossible. This is kind of cool because this is an engineering standpoint. It says that I can't make a machine which produces energy and then uses that energy to keep running forever. That's because some energy is definitely going to be lost in some of the rubbing together of materials through friction or any sound that it makes. That's a loss of energy. Therefore, this is impossible because every time it runs through, it's going to not get all the energy back that it produced. Here's the one that's kind of interesting to us because it can be finally given a connection to spontaneity, and that is any spontaneous process will increase the entropy of the universe. So if I know that the entropy of the universe has increased, then I also know that a spontaneous process occurred. Or vice versa, if the process is spontaneous, then I certainly know that the entropy of the universe has increased. And there's others. I mean, this is just a few of them. If you talk to 50 people, you're going to get probably 30 different answers to what the second law of thermodynamics is. Anyways, something important to keep in mind when you're looking at these problems is that there's a difference between the entropy of the universe and the entropy of a system. So if you see the system here, or if you see the thing that says reaction, that's talking about a specific region of the universe. And then, of course, the entropy of the universe is the whole thing. It's all the entropy that we have in the entire thing that we exist in. So, since we're talking about the universe, it might be a good idea to divide it up because the universe is a very big place. So what we're going to do is we're going to say the universe is equal to the system, the thing we're interested in talking about, whether it be a reaction, a piece of metal, whatever it is. It's equal to the system plus everything else in the universe, which is the surroundings. So they give those the two names, system and surroundings. So if your system was a rock, that would be the system, and the rest of the universe, including Jupiter, including all the other galaxies, that would be part of the universe, or the surroundings, I'm sorry. Well, if that's the case, then any change in the entropy of the universe must be equal to the change of the system's entropy plus any change that the surroundings went through. Okay, that seems fine. Well, then we can immediately write down the same kind of thing in terms of energy, and we'll use enthalpy because that's our favorite one as chemists. And this just says the energy of the universe, any change in it will be equal to the change in the energy of the system plus the change in energy of the surroundings. However, there's a caveat here. The first law of thermodynamics tells us what this value is right here. It tells us that that value is 0 because the energy of the universe is conserved. So we can immediately come up with a neat little relationship. And that is, if there's an enthalpy change, an energy change in the system, it's equal and opposite to what the surroundings is feeling in terms of energy change. That's going to be useful in here in just a second. So Rudolf Clausius was working with some engines and such, and he found a relationship between the energy flow in the form of heat, okay, from a hot object to a cold, and the temperature at which it started. So this is what he found for entropy, and it's called the Clausius Inequality. And it says any entropy change, not energy, but entropy change, is going to be greater than or equal to the amount of energy that flows divided by the temperature at which it flows. This is kind of interesting because it says the temperature matters. So we're going to end up doing things at a particular temperature, and that way we have a foundation there. We don't have two things changing at once. Just so you know, it's equal. So when we're at equilibrium, the amount of energy that flows in the form of heat divided by temperature is equal to the entropy, but otherwise the entropy change is a little bit larger than that. Clausius also made this great statement where he said the energy of the universe is a constant, which is the first law, and the entropy strives to reach a maximum, which is the second law. And that's been overstated a bunch of times, but I thought you should see it here. So let's do an example to see how this all works. And it stems from a simple experience that we've all had as humans, and that is hot things tend to give energy and warm up cold things. Or cold things tend to be warmed by hot things, however you want to look at it. In other words, there's a natural direction to the transfer of energy in the form of heat. So let's take some piece of metal A, another piece of metal B. They're going to be at different temperatures, 100 Kelvin and 250 Kelvin. And what we're going to do is we're going to let some energy flow between them. And the energy that's going to flow, we're going to just monitor the first 500 joules somehow. So as you see in my little picture here, the pieces of metal are going to be brought together so that they're touching. So there's conduction in the form of heat flowing from B to A, shown there in the diagram by the arrow. And we can start to calculate the change in entropy that occurs here. So just to remind you, since we know the magnitude of the energy that's being exchanged, all right, there's 500 joules being exchanged, and we know it's in the form of heat, then 500 joules is going into metal A because it's going to be warming, and 500 joules will be leaving metal B. And since it's leaving metal B, that's an exit, that's an exothermic type of process for it. It is losing energy, that's negative 500 joules. All right, so let's calculate the entropy for the change in entropy of metal A while this process occurs. So it started off at 100 Kelvin, then all of a sudden it got this 500 joules of energy, and its change in entropy due to that was 5 joules per Kelvin. We can do the same thing for metal B. It was given 500, it lost 500 joules, but its initial temperature was 250. So it's lost minus 2.5 joules per Kelvin of entropy. If we find the total entropy for the process, it ends up being 2.5 joules per Kelvin. Now I want you to think about that. That's exactly what we said should happen for a spontaneous process. If we put these two pieces of metal together, we would expect them to at some point reach thermal equilibrium, where their temperatures would get closer and closer to each other. Well, we're seeing here that means it's a spontaneous process, and we're getting a positive value for our entropy change, which makes perfect sense. That begs the question, what would have happened if I had started these both at, say, the same temperature, 200 or 250 or 500 degrees Kelvin? What if they were at the same temperature? What kind of entropy change would you get then? So think about that. All right, we're almost to the point where we can put a quantification onto spontaneity. We know some things about it. Reactions tend to be spontaneous, okay? They tend to be spontaneous if they give off energy. And they tend to be spontaneous if they break into a bunch of pieces. So that's the kind of things we already know, but how can we quantify it? How can we put a number to it? So let's remember that we have all these definitions about entropy of the universe, but we can't directly measure it. This is a problem. The universe is very, very large. Any device that could measure the entropy of the entire universe would have to be pretty big too. So we do know that the universe is equal to the system plus its surroundings, so maybe we can use that to our advantage. Here's how we're going to do it. We're going to start off by saying, let's use Earth-like conditions. Normally we have a constant temperature. Normally we have a constant pressure. If we did this under different conditions, we'd get a different result. All right, so now we're also going to recall one other thing, that when the energy that flows in the form of heat is done at constant pressure, all of that energy that flows as a form of heat is actually a change in the enthalpy. So this was created for you when we looked over the first law of thermodynamics. So if you can't remember this, go back and look at the thermochemistry chapter where this is discussed. We also found, due to the first law of thermodynamics, that the system and the surroundings had an equal and opposite enthalpy change for any process. All right, well, here's what we know. The second law of thermodynamics says any change in entropy for the universe is going to be greater than or equal to zero. Fine. Well, let's replace that with our surroundings and our system value. And first, let's look at our surroundings in a very interesting way. We're going to have some energy flow at constant pressure in the form of heat. All right, we're going to let this happen, but we just said that energy flow could also be called the change in the enthalpy of the surroundings. But we also just said that energy change of the surroundings is equal and opposite to the energy change of the system. Fine. All right, we also have this relationship, that the entropy of the system plus the entropy of the surroundings is equal to our entropy of the universe, so we just substitute that in. What can I do now? Well, I can now substitute my finding for delta S surroundings and plug it right back in here. When I do so, I now have this weird looking relationship, but I'm going to multiply by T, and then I'm going to rearrange it, and I'm going to get a neat little relationship which says the change in the enthalpy minus the temperature times the change in my entropy will have to be less than or equal to 0. So what we've just found is if delta H minus T delta S, if I do that mathematics and I have those values from some experiments from other things or somehow I've calculated them, if I do this and it is negative, then my process will be spontaneous. If it's equal to 0, then I'm at equilibrium. However, if I do this and I get a positive number, oh boy, what does that mean? Well, it means that the process is spontaneous, but in the opposite direction that I've written it down. That's right, in the opposite direction of what I've written down. Some people will say it's non-spontaneous. That may be true, but that would only be in the cases where we didn't have the pieces to go in the reverse direction. So we'll talk about that more later because we're going to simplify this in the future. But right now we finally have quantified how to get a spontaneity value, how to nail it down with a number. And that's been the goal of this whole chapter on thermodynamics.